Hello, this is Doug Montgomery, and I would like to welcome you to another edition of our monthly Fireside Chats. And I'll tell you, for those of you that are kind of new to this whole idea, this is something that we do to accompany the Design of Experiments course that I run on Coursera. The idea is that we have a guest speaker, and we're going to talk about some specific topics or applications of experimental design. We leave some time at the end for Q&A. The Q&A can be about anything that our speaker talks about, or it could be about anything that you've encountered in the Coursera course yourself that you would like to ask about, or it could even be a problem-specific situation that you're encountering in your work environment. And we'd be glad to try to address those questions. For those of you that are on Coursera, you will find these recordings of these fireside chats posted there. They're in the resources tab of your course. If you want to send in a question, please use the chat function on the Zoom menu to do that. And you don't have to wait until the Q&A actually begins to put in your question. You can start submitting that. You can start typing that in anytime you want to. If you don't get the question that you've asked answered during the broadcast, we'll try to respond to it in Coursera for those that are actually enrolled in the course. Now, a quick reminder about etiquette: please keep your mics muted and your cameras off during the session so that we don't get any extraneous noise or anything like that that would be distracting to the participants. Okay, it is my great pleasure to introduce our guest today, Dr. Rong Pan, who is a colleague of mine here at ASU. He is a very well-known expert, scholar in industrial engineering, and he has interests that include reliability engineering, design of experiments, time series modeling, statistical learning theory. He's widely published. He's had research projects funded by institutions like the National Science Foundation and the U.S. Department of Education. He's really a brilliant guy and one of my favorite colleagues. He, by the way, holds a PhD in industrial engineering from Penn State University. And I'll tell you something interesting about that. His doctoral dissertation advisor was a guy named Enrique del Castillo. And Enrique was my PhD student here at ASU. So Rong is my academic grandson. Okay. Now it gets even more complicated, okay, because he and I have co-advised several PhD students. So we have some PhD students that they really have a mixed parentage. It's really a mess. You know, they're his academic son. They're my academic great grandson. It's just really, you know, the family tree is just a disaster. Okay. So Wrong. We should sit down and map out that family tree sometime. just to see what all the connections.
I haven't mentioned that the family tree can be traced back to Isaac Newton.
Yes.
Remember that?
Yes, yeah. Somebody told me that my academic tree goes all the way back to Isaac Newton, which is just scary. But you and I have students that have also had PhD students, so it's really confusing. Anyway, I've taken up too much of Wrong's time, so I'd like to let him get started with his presentation. So Wrong, the floor is yours.
Great. Thank you very much, Doug. And I'm sorry I couldn't be there actually in person because I got a little cold over the weekend. So my voice, you can hear probably not that loud. But excuse me for that. Yeah, my name is Rong Pan, and I joined ASU in 2006, and since then has been Doug's colleague. And my research mostly on reliability engineering, including component reliability, system reliability, and over the past 20 years, a lot of research project has been spent on accelerated live testing. So I'm going to introduce accelerated live testing today and discuss a little bit, how the DOE, design of experiments, can be used on designing accelerated live tests. Okay. Let me share my screen. All right.
Looks good.
Great. So a very basic structure, the introduction, and talk a little bit about the mathematical model, because before you do the planning, you need to have a mathematical model, so ART model, and then the ART alt design, and then we'll have a quick summary. All right, so what's accelerated live testing, or alt? For basically this type of experiments is for studying failure and the failure mechanism. Okay, and it is to test the product to fail. Okay, and the most important response variable probably is the failure time, because we want to know how long the products will last. And typically it's lab testing, but lab testing typically referring to that you test the product under a same condition. Okay, so the stress you apply on the product is the same over the course of testing. So apply on all the products. So that's lab testing. You will not change the testing condition or stress condition to all the product. So that's lab testing in such way that you can, observe the failure time, but you will not be able to infer the relationship of the stress variable to the to the failure time or lifetime, right? Accelerated live testing has multiple purpose. First of all, if you just test the product under its normal use condition, as you know that the modern products are designed to last a very long time, okay? For a couple of years, 10 years, 25 years, and so it's impossible to test them, and waiting such a long time. So we want to, accelerate their life. So to be able to observe the failure time, sooner. So we apply stress on those product, okay? Typically the environmental stress like temperature, humidity, and voltage, current, pressure, vibration, and so on, okay? The purpose is to, accelerate the failure mechanism to be able to fail the product quicker. Okay, so that's why it's called accelerated live testing. Another purpose is to be able to study to infer the relationship between the stress variable and the product's life. Okay, so by varying those stress factors, then we can observe, how those stress factors affecting the product's life. So, by observing those life, obviously, we want to make a prediction of the product's reliability, especially the product reliability under its normal use condition. So we need to be able to infer, the actual failure time in the field. And also, in terms of the testing, live testing, it will be too time consuming, it will be too costly, okay, because you have to wait a very long time to observe a failure. A lot of time, even after waiting, many months or even years, you couldn't even observe one failure. So that basically experiments basically just fail. So to avoid this unacceptable cost of lab testing, it's another reason that we apply accelerated lab testing. All right. So I want to give you a real example what this accelerated lab test is about. Well, this is a lab-free solder drum reliability study, and the purpose is to minimize the uncertainty about the model parameter estimate. Okay, and there are certain constraints: equipment, material, time to market, and in industry, there's an industry standard over there, but we will show that those standards lead to a suboptimal model parameter estimation. Okay, and basically the acceleration model is what we call the Coffin-Manson acceleration model, okay, which is about the thermal cycle type of stress. Okay, and the Weibull distribution or Weibull lifetime distribution is widely used here. Okay, and another thing keep in mind that in this type of test, typically the exact failure time cannot be observed. You probably will observe some readout, which basically saying, by this time, by this inspection time, the product hasn't failed yet, but by the next inspection time, the product failed. So you got an interval, okay, and within this time interval, the product failed, okay, but you don't know the exact failure time. Another thing is there's always a testing period, right? So you have to stop your test at some time. Well, what about if the product, haven't failed by the time that, you terminate the experiments? Then what you observe are the survival time instead of the failure time. So those data we call right censored data. Okay, so censoring is really a real concern here. Okay, in live testing or accelerated live testing, we have to have a way to to figure out how to handle censoring. And censoring basically give you incomplete information about the response because you don't have the exact response, but some type of interval response or right censored response. All right, for this particular experiment, our objective is to compare the influence of design matrix with other design factors such as censoring, and to identify the design that reduce parameter estimation variance, for example, using the D-optimality criteria, which is a special type of optimum design. So the test is like this. Here's the equipment. They basically is a heat chamber, okay, and it has 3 chambers, okay, and this chamber, for example, is setting at certain temperature. For example, it's hot chamber, and middle chamber could be a cold chamber, and the bottom chamber is a heat chamber again, and parts will be put on those trays, right? And you can see a shaft here. So those trays will go up and down, okay? And the cycle on those 2 chambers, each tray will be cycled in those any two chambers. So that create this type of thermal cycle, okay? All right, so this is the temperature, all right? And by this thermal cycle, you can see there are several parameters. For example, how long the part will stay on the high temperature, okay? And how long is one cycle, and what's the delta T, the temperature difference, okay, between low temperature and the high temperature, okay, and those parameters are the design parameters, right? And those parameters will affecting the lifetime, okay, of the product, okay. So you can see that this design is a multi-factor design, okay. At least there's 3 factors here should be considered when you design this type of experiments. All right, and because of the equipment, material, and the time to market, there's always some constraints that you have to consider. For any experimental design, as you know, there's always some, type of practical engineering constraints. The design factors cannot be, larger than certain value or below certain value. Same here. For example, the material, the high temperature couldn't be too high. Otherwise, the material will melt and the failure mode will change. Okay, and same for the dwell time, and the equipment has its constraint also. The low temperature couldn't be too low, or the high temperature couldn't be too high. So, and also another constraint here is we want to get some result quickly because it's accelerated test, right? And the reason of doing accelerated test is to shorten the time, all right? So we want the acceleration factor to be larger than 3.5. Okay, so that translates to no more than 6 months test. Okay, so if you plot all those constraints, okay, this is actually a 3-dimensional, just project the 3-dimensional. You can see those constraints give you a very irregular test region, okay? So using the regular factorial design or fractional factorial design, probably not very suitable here. It's hard to fit. All right. I already mentioned several challenges, but summarize here. Failure time data often censored. Okay, so the information you got from those type of experiments are basically a lot of incomplete of failure time or incomplete data. Okay, failure time distribution is typically not normal. Okay, Weibull distribution or exponential distribution very common, and also log normal distribution are very common too. And another thing kind of special to this type of experiments is a lot of time you have, well, most of the time actually, you have to do the extrapolation, okay? Because we want to know the use condition failure time, okay? By doing the accelerated lab test, and the test result, the failure time is under the accelerated condition, not the use condition. So to obtain the use condition failure time, you have to do this extrapolation. So it must be model-based extrapolation. So that's why building the model is very important. An accurate and robust model really affecting the extrapolation error. So that's why to be able to estimate the model as precise as possible is a very important and very difficult job to do. All right. As far as I can see, so the DOE principle hasn't been used much in the our testing plan yet, because could be, due to the limitation of test equipment. A lot of time, this type of test just test for one stress factor. Okay, so it's really just the one factor design. Okay, and but as you can see in the previous example, now the equipment become more capable. A lot of parameters, design parameters can be changed, can be designed. Okay, non-normal distribution that violate the typical DOE model, and nonlinear acceleration model. Okay, those acceleration models oftentimes has some physical meaning. So those physical acceleration model are typically nonlinear. And censoring, we mentioned, time cost constraint, and also in terms of extrapolation for prediction that increase the uncertainty. All right, so practical motivation, the profitability of company, and all these benefits can bring to the company by producing reliable product, obviously. All right, let me quickly jump to ALT model. I want to mention a couple of books related to ALT, like the Nelson's book. That's the classical book in this ALT field, accelerated testing. Okay, and also Mika Escobar's book. And in terms of DOE and GLM, Doug and I, and also Dr. Regan, Dr. Freeman, we have a book called Design of Experiments for Reliability Achievement, published 2022. Right? So what type of acceleration model? One type of acceleration model is acceleration factor. Okay, basically is to enlarge the time. Okay, from the accelerated condition, the failure time at accelerated condition enlarge them to the use condition by this acceleration factor. And this acceleration factor can be quantified by some physics model, like Arrhenius model, inverse power model, E-ring model. Okay. And in terms of the failure time distribution, as we said, Weibull distribution is the most commonly used. Okay, and the Weibull distribution have this type of hazard function. Okay, not the entire, what we call the best top curve. Weibull distribution can model all those three stage. Okay, not with one single model, but with different Weibull model, it can model all these three stage. Okay, and by those physics model, the failure rate, for example, in the middle stage, where the failure rate is constant, okay, and basically that's the exponential distribution, right? So here, those physics model, the log failure rate can be modeled as a linear function of those stress factor. Okay, although depends on different stress model, those x1, xk, they could be transformed from the original stress factor. Okay, by for example, a linear transformation or log transformation. But still, you can see this is a log linear function. It's a nonlinear function. All right, so suppose that we already collect the failure time data or censored data, okay? And how we analyze it, how we do the parameter estimation. You know, the typical way is to do the maximum likelihood estimation, all right? So how to form this likelihood function, okay, for different kind of data, you know, exact failure time, right censoring time, or interval censoring time. Well, for exact failure time, you use the information come from the density function. For right censoring time, is the reliability function, and the interval censoring time, it comes from the probability of failure, you know, during that interval, okay? And construct this likelihood function and maximize the log likelihood function. Okay. However, we take a different look of this likelihood function. Okay. If you go through this formula, okay, and eventually what you find here is this part is like from a Poisson distribution with parameter mu, okay, with this mean parameter, the Poisson's mean, mu, okay? And here, this part is just has nothing to do with the parameter, okay? It's just the observation. Well, let me explain a little bit. This C basically is an indicator variable saying it failed or not fail. Okay, so the part either fail or not fail. That's the right censoring case. Okay, and mu will be equal to the failure rate times y. Y is the failure time or the censoring time. Okay, so it's your observation. Okay, and k is the index of the part. Okay, so from the likelihood function, you basically have two parts here. One is the likelihood of the Poisson distribution, and another part is, a fixed part or offset. It does not depend on the parameter lambda. All right. So to maximize this likelihood function, it's like treating your data as from a Poisson distribution, not the data transferred to an indicator variable for censoring. Okay, so it's like you're counting the censoring indicator variable and treat it as from a Poisson distribution. So that's the case for the right censoring, and for interval censoring, is like you're counting from a binomial distribution how many failure during certain interval. Okay, and by looking at this data structure, we can formulate the ART to a generalized linear model. Okay, and by generalized linear model, we are able to design for the generalized linear model. Okay, that's a little mathematics, but here we have an offset, which basically is this constant part. Okay, has nothing to do with parameter. Now, in terms of design with generalized linear model, okay, and we can formulate the feature information matrix of the generalized linear model, okay, and the D-optimum design basically is to maximize the determinant of information matrix. Okay, D-optimum is related to the model estimation. right? And model parameter estimation, try to be able to estimate the model parameter as precise as possible, basically minimize the variance of the estimator. Okay, that's the optimal design. And there are other design purpose, for example, what we call the U-optimum design, because eventually you want to predict the reliability at the use condition. So the design purpose could be minimize the variance of reliability prediction at the use condition, or I-optimum design to minimize the average variance of reliability prediction over the use stress region. Okay. Now, take this example. Let's say we have two stress factor, okay, temperature and the humidity, and with a linear law and the inverse power law. For a linear law typically is for the temperature, okay, and the inverse power law is for the humidity. All right, and with this, and also assuming they have some small interaction. All right, and here's our design region. Okay, remember that is a survey test, so the use condition is outside the design region. Okay, and you do the experiment here, and you want to predict here. Okay, which is outside the design region. All right, so if we do different design, okay, one is a split design, which is based on Mika Escobar's book, okay, and that's what this design looks like. Okay, here's the design region, okay, and it will choose 3 design points, okay, do 3 experiments and how they allocate a test unit at each experiments. And if we do the optimum design, that's what the design looks like. And the U-optimum design, that's what the design looks like. Okay, and want you to pay attention to the design. You see the number of test units sort of more evenly located at 4 design points, right? And this design try to cover as much as the design region. Well, for U-optimum, because it's for prediction purpose, here, this point more close to the use condition, and it locate more test unit here, okay? Because here, make your prediction more, more closer to the use condition. And we also, drawing this variance curve and to a contour plot and to illustrate what the prediction variance looks like for different type of design. And you can do sensitivity analysis by varying model coefficient and to see how the design will change. And this is 2-factor design. And from here, you can also discuss, what's the mitigation strategy in terms of making the design more robust. But I want to get to the previous example, the Soder-John study example. As I said, the industry has their own standard, okay? And that's their legacy design, okay? And from here, you can see the design efficiency is really low, okay? Less than 1%, okay? And you can see this 4 design point covers just a very small region of the whole design, okay? If we sort of fitting a orthogonal design, a factorial design here, okay, and it will increase the efficiency quite a lot, 38%. But if we can design a d-optimum design, okay, and the efficiency will increase to 74%. All right, that's another comparison of those three types of design: legacy design, orthogonal design, and the d-optimum design. The general conclusion is your prediction estimation variance, okay, becomes smaller with d-optimum design, and obviously if you have complete failure time data, it will be smaller. Okay, the variance will be small. But if you have our interval type of data, okay, the estimation variance will be larger. Okay. All right, let me summarize it. So basically, we talk about modeling art and the connection of design experiments to art, and hopefully that you can take away from this talk. I mean, for analyze this type of data, art data, the data structure is important. Okay, how you look at the data structure, from failure time point of view or from censoring point of view. Okay, and those type of experiments has a lot of engineering constraint, and there's some design dilemma. For example, you have to know the model parameters before you do the design. So it's better to do the sensitivity analysis after you form a design, and to evaluate how sensitive your design will change if the parameter assumption is it's not exactly what you think about. Okay, and also there are some computational challenge, and this type of design has, as far as I see, has not been fully implemented in commercial software. Okay, even Jump, it has some function, but not really doing the true optimal design, in my view. All right, some general suggestion to art planning. Okay, so one is understand the purpose of your experiments, anticipate data censoring, and assess the robustness of test plan, okay, to the assumption, and be aware of the model extrapolation, and plan for the uncertainty of use condition, and incorporate practical engineering and management constraint into the plan. Here are a couple reference. All right. Thank you so much.
Rong, thank you very much for this talk. This is a very informative talk. I want to ask you a question that sort of came up toward the end of the talk, and that has to do with software. If you wanted to implement these ideas, what do you recommend that people look at in terms of software that might be useful?
Well, I mentioned Jump, right? And Jump, although it has some limited capability, but it's still probably the top of the line. Okay, as far as I know, for art, it can handle up to 2 factors.
Mm-hmm.
And it can handle probably up to the second order model. I think probably not second order model, probably the first order with interaction.
That's my understanding as well. For people that are really interested in looking into that, let me suggest that there is another Fireside chat that is available. And the person that did that was Caleb King, who is with Jump, and he's the developer in charge of their alt platform. And he took us through sort of a pretty complete demonstration of how that alt platform works. So that might be a good follow-on for people that are interested in this to explore. Your talk is really interesting. The thing that I have always found fascinating about this is that, you know, in many cases, you want to build an experimental design, excuse me, that enables you to make the best predictions at an extrapolation point, which is, you know,
Yeah.
which is really, really interesting. And that is a very complicated mathematical problem.
Yeah, yeah, certainly. And you know, complicate more is the, you know, nonlinear, non-normal, and this model parameter dependency problem in optimal design. So everything add up.
Yeah, yeah. And there has been a question that has come up that says, can you do this type of design analysis with Jump or Jump Pro? And yes, you can to a degree. To a degree. The Jump alt platform does enable you to have two factors, up to two factors, and the basic model that they consider, if I remember all the details from Caleb's Fireside chat, it allows you to deal with the two main effects and a two-factor interaction.
Another constraint I see in Jump is you sort of have to give them an initial plan.
Yeah,
So you have to tell them, you know, how many design points.
right. Yeah, it wants to know how many. Well, it wants to know how many units you're going to test.
Yeah, how many unit and how many design point, and
Right,
what are the location of those design point.
right.
And what we can optimize is, you know, how they are going to how to allocate the
Right,
test unit to those location.
right. You specify the levels of each of your acceleration factors, say low, medium, and high, and that determines the basic structure of the design, and then the optimization is in allocating the units. Again, that's my understanding of how that works.
Yeah.
It's a nice platform, but it's a simplified version of the problem that you're talking about here.
Yeah.
Um,
But
but
in our book, we also have we mentioned this R package
mhm,
that is called alt op opt
right,
optimization.
alt opt, yeah,
Yeah. So that package sort of can give you the D optimal design or U optimal design. And it has certain limitation too, I think. Probably I don't know, up to 2 or 3 factors. But it gives you a more optimum type of design, I would say.
right, right.
Too optimal.
Yeah, I remember that. I remember that part of the book does have some discussion of the R code, and so maybe that would be another option for this individual to explore would be to look at the R code, and we have a pretty good discussion of that in the book. It might be a good place for them to
Yeah,
start.
yeah. There are some example you can try.
Right, be a good starting point for that person to look into. And I don't did you had our book as one of the references, right?
Yeah,
Yeah, okay, good. So they could track that down without too much excuse me, without too much difficulty, or no pun intended, without too much stress. Yeah, it wasn't that funny, was it? I thought that was pretty good. Okay, so that was a good question. I appreciate that question, and I particularly appreciate it because it gives a link back to another fireside chat that people might find informative if they liked what's going on here. So thank you for that. Okay, let's see if we've got any more questions that have popped up. Here's one. Why the factorial design experiments for media optimization? This is in biotechnology, needs lots of experiments and replicates, like 7 factors as an example. Well, I've done some consulting work for biotech companies where the media development is part of the problem. One of the reasons you have lots of factors is that these are very complicated phenomena that you're dealing with. There are lots of for example, there might be lots of ingredients in the particular media, or lots of other factors that affect its performance. So they're complicated phenomena to begin with. Fractional factorial experiments can be useful. For example, the 7 you mentioned 7 factors. 7 factors in 16 runs is a resolution 4 experiment. So from that, you're going to get estimates of all of the main effects, and you're going to learn something about the 2-factor interactions. And so that would be a way to reduce the amount of testing that might be necessary. The other thing that you might consider would be non-regular designs. There are non-regular designs with 7 factors and 16 runs that allow you to estimate main effects and some 2-factor interactions, clear of other 2-factor interactions. They're better than the traditional resolution 4 designs. So you might want to look into those. And some of those designs are in my textbook, which is the reference book for this course. And there is a published literature on that. If you sent me an email, I could point you to some specific journal papers. Why lots of replicates? Well, because the phenomena you're experimenting with is often pretty noisy. The response variable there's a lot of variability in the response, and when you have a lot of variability in a response variable, you're going to typically have to have more replication in order to counter the variability. It's a signal to noise kind of issue. You know, if the signal is weak because there's a lot of noise, the way you have to counter that is with additional observations, more replication. Some of these media optimization problems have been mixture experiments because you're formulating the media, and so I've seen some of these that are mixture experiments, some of them that are mixture process variable experiments. So they can get pretty complicated. And that's why they often have a moderately large number of factors. Rong, do you have any comments on that? You've done some work in this area too, I know. But
Well, mixture experiments, in my view, basically add in some constraint, a special constraint, because you have to have the formula
right,
add to 100%. So so the design space is not the regular, right? Is this simplex design space.
right.
So when you consider this design space and to find the design points, and you have to think about if you use just a single point. I mean, in this, for example, if you have this triangle, each single point will be just one ingredient. Okay, so you cover the whole space. You can use 3 points, these 3 vertex to
Right.
cover the whole region, but that's just one ingredient. it will not give you any information about, how the ingredient will interact with each other.
Right.
So that's really probably something you want to know, right? So there's a lot of interesting design in these mixture experiments. So I would say Cornell's book and on mixture design is a very good reference book.
It's really the classic book on the subject. John Cornell was a faculty member at the University of Florida, and I recommend his book to everybody because it is the classic work on mixtures. John passed away a few years ago, and so there has not been an updated version of the book since then. But someone should update that book because it is really the classic. An interesting story about him. John Cornell and I went to graduate school together. He lived in the apartment next to me at Virginia Tech in Blacksburg. So we had a common wall between our apartments. And so I learned a lot about mixture experiments just by osmosis because John was right next door, and he was doing his dissertation on mixtures. And another interesting thing about John, he was a lunatic golfer. He played golf all the time, and so was I. And we were constantly playing golf on the Virginia Tech golf course. And if it was 40 degrees or warmer, we were playing golf. And we played so much golf that it became questionable as to whether we would ever get our dissertations finished. but eventually we did. And John and I played golf many times over the years because whenever we were going to conferences, we would always take our golf clubs and we would try to find a way to blow off the conference for a day and go play golf. So I owe a lot of what I know about mixture experiments to John. And in a lot of these biotech companies, many of the problems that you do have to deal with in media formulation are mixture problems. And some of the companies that I've done consulting work with for in that area, the scientists there didn't recognize that the problem was a mixture problem, and they were trying to do this with factorials. And that generally doesn't work. You generally cannot attack mixture problems with factorial experiments and get good results. There is material in the MOOC on mixture experiments, and I would encourage you to go away and take a look at that material and see if some of that might be helpful in resolving the questions that the issues that motivated the question that we're talking about. Okay, we have one more question here that I can see, and oh, this is wrong. Can you read this? This is complicated. How can design of experiments be effectively applied in investigating and addressing the recurring failures in an aging crusher within a mining operation, particularly considering multiple factors such as bearing issues, motor problems, excessive weight on belts, and so forth? And the goal is to gain a comprehensive understanding of the system and minimize unplanned production downtime, recognizing the significant cost implications associated with each hour of interruption or intervention for testing in the context of this large-scale machinery. Boy, this is a complicated problem.
Yeah. Well, the first thing come up to my mind, if the problem is too complicated, let's simplify it. I mean,
Yeah.
the systems has components. You mentioned a couple of things, the
bearings.
the bearings, and First of all, let's figure out which one is the which one is the number one. Okay, the number one bad guy. Okay, and probably you will use a FMEA. That's very
Right.
common tool in engineering and management.
And,
Use
and you may have some historical failure data too
correct.
that
Yeah.
you can wrap around this. Yeah, that's
Mhm. And after you figure out that, identify the number one bad guy, and pick it up and look at how they fail. Okay, do some research on the failure mechanism. Okay, it could be failed by material. It could be failed by wrongly applied stress.
Mhm.
It could be, if for example the rolling is not designed to stand for such pressure, and but during operation it was applied on those high pressure, then it will cause failure. So you probably will think about, maybe I should replace this component and test some other component, some other parts with different material. So I think it's sort of a common sense approach, get down to the failure mechanism, okay, and then we can talk about how to design the experiments to test and to compare different product.
Right. Yeah, I think your suggestion of failure mode effects analysis as a starting point is a really good suggestion. And again, hopefully there's some historical data that can help drive that, and try to understand what the key failure mechanisms are in this kind of system. But this is going to be a big job. It's not going to be easy. I think we have come to the end of today's questions, and that's pretty fortunate because we're just about out of time as well. Our next Fireside Chat is going to be in February 2024. More information about that, including the date and the guest, is going to be posted in Coursera pretty soon. I mentioned during this Fireside Chat a previous one that you might want to look at. You can find the past recordings in the resources tab in Coursera. And I would strongly suggest that you take a look at the one that we referred to as a great accompaniment for Rong's presentation. Caleb King did a very nice job and gave a good jump demo that I think would be useful for you. So with that, I'd like to thank everyone who came today. We had a good turnout, and we look forward to seeing you later on.